I'm Indira Chatterji from Nice. She'll be talking about old results and new questions on the rapid decay property.
Well, thank you very much for the invitation. It's really nice to be here. And my talk today is about the rapid decay property. I wrote a survey introduction on the subject not so long ago. And what I wanted to discuss here is things that I didn't put in this introduction, mainly because when you write an introduction on a subject, you have to stay focused. And so while writing it, originally I had the project of writing a book. That was 15 years ago, and that never happened because I didn't know what kind of generality I should be in. So each time I tried to put a little more generality, I would get lost. And so this didn't happen. So right, okay. But I still won't only say what's not in the introduction because I still need to introduce it. At least I know that some people don't really know about it, even though some people know it well enough. So okay, so rapid decay property. So I'm going to take a discrete group. G discrete, finitely generated, and locally compact, compactly generated is okay. And so yeah, so G locally compact or compactly generated, also okay. And I'm going to take a length function, which is a map from G to R plus, and that satisfies that the identity is 0 and it's subadditive. And LG is LG inverse, so that's a length function. So for instance, the word length, but any action will do. Any action by isometry on the metric space will do. And so this is going to be the ball of radius r. And CG for me is going to be the functions from G to C with compact support, which means finite support, since I'm thinking that my groups are discrete. And so G has the rapid decay property if there exist constants 1, 0, such that for every f in CG supported on the ball of radius r, we have that the sup norm of f is bounded by a constant times the L2 norm of f. So what is that? Yeah, so that's one definition. And so what is that? What is that norm? It's the operator norm of f acting on L2 of G via its regular representation. And yeah, so the plan for the talk is first I'm going to explain the case, what happened in the case where G is equal to Z. And maybe give some motivations for studying this property. And then I'm going to discuss some old results. And maybe I shouldn't have said new questions because, well, hopefully they're new to you, but maybe they're not that new. I should say open questions. Some of them are new, but what can you do with the old questions, right? All right, so just a word about the definition. I'm going to give equivalent definitions. I'm going to give equivalent definition, but this is my favorite, my personal favorite definition. So why is it? Because you can see that this thing, which you may or may not like, if you're doing geometric group theory, some people don't like it. People from operator algebra, they love it. So what is this? This relies heavily on the group structure. Because, you know, you act via the regular representation. What do? If you take a Dirac function in L2, the regular representation is going to move it according to the group law. So this relies heavily on the group law. And this side relies on the geometry of the group, because this doesn't care about the group law. The L2 norm, you know, L2 doesn't even know that you're in a group. L2 of G is L2 of N until you start moving things around. And so this doesn't even see the group structure, and this sees it in a geometric way because it just only records the size of the support in terms of the length function. So that's the reason why I like this definition. But this is not Kahn's original definition. Kahn's original definition it's equivalently. So equivalently, that's Kahn's original definition. The rapid decay functions are contained in the reduced C-star algebra. So this is the rapid decay functions, and this is the reduced C-star algebra. So that's Kahn's original definition. And yeah, that's Kahn's original definition. So let's look at this original definition on G is equal to Z. So what happened on G equal to Z? So if you do Fourier transform, Z corresponds to its Pontryagin dual, which is S1, right? So here you have Z and you get S1. And what's the map? Well, you have a Dirac. Oh, well, the map is just sending n to z to the power n. Right. So under this, you have that the function with finite support correspond to Laurent polynomials, and in fact, a function with finite support is of the form fn delta n, with n is the Dirac function and n. So it takes n and it gives you 1. So a function with finite support is a bunch of points, finitely many points over z, and that gives you f of n zn. And if you look at what happens to the star norm, the operator norm, it's just giving you the sup norm. Well, I should write x. Anyway, it's the sup norm because the Laurent polynomial is a continuous function. So if you have a continuous function, you take the biggest value, and that's going to be your sup norm. And if you continue with this identification and you complete with the L2 norm, you can do that on both sides. you have an isometric isomorphism between L2 of Z and L2 of S1. And you have a C star algebra isometric isomorphism between the reduced C star algebra of Z and the continuous function over S1. And this function, this algebra of functions with rapid decay, they correspond to the smooth function over S1. And so here you can test Alencon's original definition easily because you have that the smooth functions are contained in the continuous function. That's pretty standard. So this can seem pretty basic, but in fact, when I was writing this survey, I tried to understand really those correspondences, and notice that here you already find some pretty tricky questions that people don't really understand. You're given a continuous function. When can you approximate it using the Fourier series? And that's not always the case. You can't be too naive here. And okay, great.
Excuse me, Indira. Am I right that the first definition it's right away true if the group has polynomial growth?
Yes, I was going to say it. Yes. That's part 2 of my talk. But yeah, exactly. The first one, you can the first one. Well, if you've played enough with this operator norm, if the group is polynomial growth, you can see that this. Well, no, that's what's always true is that this norm is bounded above by the L1 norm. And if the group is polynomial growth, you use Cauchy-Schwarz to say that the L1 norm is going to be bounded by the cardinality of the Boole square root times the L2 norm. Indeed, it's pretty straightforward if you have polynomial growth. Right, so the motivation is in, that was the Kahn's original definition. And then right, so the property gained a lot of traction with Vincent Laforgue's result in 2000 because he was working on the Baum-Kahn conjecture, and he proved some, anyway, I'm not going to go into the Baum-Kahn conjecture, but many interesting groups. So he managed to give the first example of groups with property T satisfying the Baum-Kahn conjecture using this rapid decay property. And for many interesting groups, the rapid decay property is the missing piece to understand the conjecture. So, right. So, uses of the rapid decay property. But I'm not going to talk about that. I wanted to mention another use of this property in the context of random walks. In the context of random walks, if you take a random walk is in fact just an element in CG, which is symmetric if your random walk is symmetric. When you take the 2n convolution, well, if you like to think of CG as an algebra, it's just the 2nth power that you evaluate in E, that gives you the probability of return after 2n steps according to this random walk. For instance, think of the weighted characteristic function of a generating set. And so this, in fact, tends to 0 exponentially fast if G is non-amenable. So when G is non-amenable, looking at this quantity is doesn't give you much information. But equivalently, G non-amenable means that the spectral radius of F is greater than 1. So you can look.
Smaller than 1.
Oh, yes, thanks. Smaller than 1. So you can look at the function phi f that maps n to rho to the minus 2 n f times, right? So you take this return probability and you adjust it with the spectral radius. And it's pretty easy to see that it's always Cn inverse. You always have this. That's standard. Well, that's not. I'm not saying that you should see it. I'm saying that you can find it in the literature at several places. And an observation that's not very difficult to do is that if you have rapid decay, if your group has rapid decay, then this is bounded below by Cn to the minus 2d, where d is your rapid decay constant. So in some sense, this is interesting. So why do I mention that? Because that's kind of a question that you might wonder if you're thinking of random walks, and random walks gives you and rapid decay give you kind of constraints on the possible behaviors of your random walks. And for instance, recently Guézel showed that the asymptotics for this function is the right asymptotic for this function is 3/2, and rapid decay property we will see later gives you the bound -1 and -3. It's not so bad, but it's not optimal, but it's much easier than Guézel's work. All right. So since I was, so I have one more equivalent definition, actually two, that I wanted to point out, which is that, which is what? Oh yeah, that there exists C and D constants such that for every R in N and every 2 elements in L2 of G of norm 1, then the sum of gamma in the Boloff radius R of the coefficients for the regular representation squared is less than or equal to C times R to the 2D. So this characterization is due to Mattia Perrone, and it's a variation of another characterization that's due to Emmanuel Bruyat, and that says that there exists M, a constant, and k greater or equal to 0, such that for any C n in L2 of G of norm 1, the sum gamma in G of the coefficient of the regular representation is there a square here? I think I should put a square. 1 plus L gamma to the to k is less than or equal to m. So those are all equivalent definitions. And this one, and the last two ones, so this one was suggested by Emmanuel in 2005 when we had a workshop on it. And it's the one where that kind of tells you straight away that maybe you should be looking at other representations than the regular representation. Right, so that's another equivalent definition. Yes, so this already tells you that maybe you should look at other representation than the unitary representation. And another thing that you can also do is vary the length function. That's another thing that you can do. But if you have rapid decay and you have another length function, you see pretty quickly that you will have rapid decay with the group for the word length. I mean, that's an exercise that's pretty easy to do. And right, so let me just tell you about all the results, and I mean known results, because geometric group theorists always want to know, if their favorite group satisfies this property or not. Okay, so known result. So as Stefan already mentioned, G with polynomial growth and another thing that's a result by Jolissin. In fact, so Kahn gave this definition, but Jolissin really studied it using a variation of that definition, or something that's right in between those two definitions that I didn't put on the board. But he really studied and proved many fundamental results, including the first one, which says that if G is amenable and has rapid decay, then it has polynomial growth. And you can see it right away if you do, right, yes. So to see that, you take f is the characteristic function of a ball of radius r. And amenability, one definition, I think it's Leptin's definition of amenability, tells you that in this case, the sup norm, the operator norm, is given by the L1 norm. And so that's the cardinality. So that would be then the cardinality of the ball of radius r. And now if you assume that you had rapid decay, you're bounded by this times the L2 norm, but this is then the square root of the ball of radius r. So that forces the ball of radius r to be bounded by a polynomial. And so that's already a pretty strong negative result, because it's inherited by subgroups. And in fact, it's inherited by subgroup with the induced length. So each time you have an exponentially distorted copy of Z, for instance, that rules out the rapid decay property. And so it implies that SLN Z for n greater or equal to 3 does not you can find tons of amenable subgroups there that have exponential growth. Right. So let me just let me tell you about G is equal to F2. So that was Hagerup in his paper that started both the Hagerup property and kind of also started rapid decay property, because he proves both results. So so yeah, to look at the case G is equal to F2, I'm going to prove a variation of that. So you will show that for any f g h in R plus G, and the support of f is contained in a ball of radius R, you have that f convolution G convolution H in the identity is less than or equal to C or D times the multiplication of the L2 norms. So it's not very difficult to see that this is actually the same thing as this definition, right? Because when you take the soup, you add this one guy and then you put it there, and then when you take L2 norms, it's actually the inner product. And if you think about the inner product, when you develop the inner product, it's that. So anyway, it's another equivalent definition. Yeah, so this is where my talk is good with the conference. It's going to be an approximation of the proof. It's not exactly a proof, it's an approximation of the proof. So if you develop that, you're going to get the sum of x, y, in F2 of f of x, g of y, h of y inverse, x inverse. And you're in a free group. We're in the free group. So we already see here something that is, I think, very interesting in this property, is that you're dealing with triples of points. And so you're in a free group. So you're on the tree. You have x, y, and x inverse, y inverse somewhere here. So you have a unique point T, which is a median point. And so that is going to be the same. If I sum over x, y in F2, maybe I'll add some more, but it's going to be the same as if I sum over all the median points of x, y, y inverse, x inverse. Because there is only one. So maybe I add something which doesn't really matter, because the inequality is going to be in that direction. And this is where the magic happens. You can express that as the trace of the composition of three operators, where your operator is going to be from L2 to L2. So you give this operator in a matrix form, di dB is going to be f of A inverse B if you have the situation that A identity and B is a geodesic, and 0 otherwise. And then you use something that's not magic and that's pretty well known, is that this can be bounded by the Hilbert-Schmidt norms of those operators. And when you compute this Hilbert-Schmidt norms, when you compute the Hilbert-Schmidt norms, you will see that those are bounded by, in this case, square root of r times f2, and the same for the others. I'm not saying that you should see it. That's the approximation part of the talk. But this is where you get well, that's not very surprising in this case, because this is going to be 0 if A and B are too far apart. So what are going to matter is how many points are on the geodesic between A and B that are at distance r. And in fact, so that's for the free group case. And in fact, if you do a quasification of that proof, you get word hyperbolic groups. Because what you do is here you're going to add points that are almost on geodesics, and then here you're going to count how many points are on a geodesic between 2 points. So that's a quasification of that proof that gives you word hyperbolic group. And another deformation of, there's not even of the proof of the assumptions, gives you the following criteria, which is that if G acts on a metric space XD, which I'll call discrete, and I want uniformly bounded stabilizers, and such that for any x, y in X, there exists a set C of xy, a subset of X. So it's a subset of X with xy in this subset, and such that for any xyz, C of xy, the triple intersection C of yz intersect C of zy is non-trivial, is non-empty, and you want the cardinality of C of xy intersected with a ball of radius r to be bounded by some polynomial in R, and you want also the diameter of C of xy to be bounded by another polynomial in R. So then G has rapid decay. So that's a good example of a result that cannot really be attributed to anybody, because it appears the first time in my paper with Kim Moraine when we were doing lattices and non-uniform lattices in rank-Brownlee group, but the proof is exactly the proof for hyperbolic groups. There's nothing to change in the proof. It just works out of the box. And
CZY or CZX?
CZX, thanks. And this already gives you an interesting class of group. This gives you an interesting class of group. For instance, G acting on a coarse median space, Bowditch, or Burstock-Minsky did mapping class group. Well, they didn't really do it like this, but that's one way of seeing it. And right. So one result that this doesn't cover, for instance, is the following theorem.
You need finite rank for force mediums.
Oh yeah, sorry, finite rank. So one result that it doesn't one class of group that you can't get that way, I think, is this. So that's Ramager, Robertson, Steger, Laforgue. That says that if gamma is co-compact in SL3K, K is R QP, R C H, and there's another guy. Then gamma has rapid decay. So you can't get it that way. And in fact, the way they do is an iteration on that idea. Basically, they use the geometry of SL3 to take this computation over triple of points and reduce it to triples that are easier to deal with. And the geometry of SL3 allows you to do that. And another instance where this idea of taking triples and reducing it to triples that you can compute is the result by Drew to Sapir for G hyperbolic relative to H with rapid decay property implies G has also rapid decay property. It's the same idea. You take triple of points, use relative hyperbolicity to reduce it to triple of point in a group that already has rapid decay property. So in some sense, it's easier than what those people do. And that's pretty interesting because Ramager, Robertson, Steger, they're the one with the interesting computation. They really have the interesting computation. And what Laforgue does is he quasifies this proof. And that kind of brings an interesting question that I could never really give a good answer to. So what he does is really quasifies their proof, but is there like a mathematical statement that says that in some sense symmetric spaces are quasifications of buildings? I mean, people think like this, you know, they do stuff for buildings and they're like, oh yeah, I'm going to do more or less the same thing on the symmetric space.
You can say the asymptotic cone is a building.
Right, you can say the asymptotic cone is a building, but I wanted something in the space. I wanted to not go all the way to the asymptotic cone. I wanted something on the vein of Gromov's tree approximation theorem, but where you would approximate things not with a tree, but with a piece of a building. And this is what Laforgue does, but he only does it for SL3 and for 4 points. So, but his way of doing things does not extend. Definitely not. So, yeah.
You have a statement in first order logic.
Ah! That's already, you lost me there already.
Pulling back to
So, right. And right, so that brings already to that. Yeah, that's obviously, and that's not a new. That's definitely not in the new question part, but it's still in the old result. it's the conjecture U2 Valette. Although I'm not sure it's, yeah, well, did you really conjecture that? That gamma co-compact in SLNK for n greater or equal to 3 has rapid decay property. And right, so yeah, so K is R QP or other, yeah. And so yeah, that's open. And I know people who died mathematically obsessing about this question.
Wow, it's good propaganda.
So, and so there's a naive attempt for that, which is it's not very hard to see that you have that SLNR has rapid decay property. That's not very difficult to do. It's actually Kuenzer-Stein phenomena. When you understand Kuenzer-Stein phenomena, which we didn't, so we redid it. But there are several very nice proof of the fact that it has rapid decay property. And also one thing that Jolissen did is to show that if you have a lattice that has rapid decay, then the ambient group inherits it. So you would like to know, does it go to co-compact lattices? And so that's the first naive attempt that usually doesn't work. And usually when people try to do that, at some point they mix left and right, and they get a proof. So that's usually how wrong proofs go. So let me just go to, well, I should have put that on open questions. So, right, so that's definitely, oh yeah, so before, yeah, I'm going to go back to the other, looking at other unitary representation, but before I do that, there's one group for which it's been open, it's still open, is out of n. And one approach that's probably not going to work is the following question. Right, if G is acylindrically hyperbolic and points stabilizers have rapid decay property, then so does G. So I don't know, that's the naive way of proving that is not going to work, mainly because when you, so acylindrically hyperbolic means that you have an action on a hyperbolic space, so then the stabilizer can be big, but if the stabilizer far away, but the stabilizer far away don't intersect much. So point stabilizer can be big, but if you go far away, things that stabilize both ends won't intersect much. But the problem is that this doesn't ask for any local finiteness of the hyperbolic space, so the naive things you want to do is not going to work. Well, you can try again. Maybe you're less naive than me, but right. But that's too well. If somehow you have a little more assumptions on the hyperbolic space you act, maybe you have a hope. And but I guess the first thing to do would be to try and put the mapping class group result, which is already known, and to do it for this setting and to see if that can be then carried over to out fn. But otherwise, no idea how to handle out fn, obviously. And right. So what Breuillard already suggested in 2005, and that Adrien Boyer, who's a student of Christophe Pittet, started, is study rapid decay for other representations. So for instance, Uri Bader's unitary representation that he discussed yesterday. And so the remark, so why would that help? So there's one thing that would maybe help, but I think that that Boyer's work shows that it probably won't help. But I mean, it doesn't. Well, anyway. So why would that help? So the following reason, there is a definition due to Shalom that says that if you have pi, a unitary representation, and you have Xi in H is a positive vector, if this thing is greater than 0 for all Xi in H. And then Shalom has a lemma saying that if you have a representation with a positive vector, then it's always bigger than the regular representation. If pi is a representation with positive vector, then it's always bigger than the regular representation for all f in CG. So as a corollary, obvious corollary, if you have rapid decay for a representation with a positive vector, then G has rapid decay property for the definition, for one of the definition that I gave. So that's what Boyer does. He finds a bunch of he studies other representations. He studies he studies that kind of inequality for other representations, and one thing that he shows, for instance, is that for SL and Z, they never have rapid decay, even though they have positive vectors, which is good. Because we didn't expect SL and Z to have rapid decay. We already said they wouldn't have it, but right. All right, Another comment that I'm going to make in the last minutes is that so you saw that here you have constants. So here it's I think is the same constant. Here I put another k, and there is a definition that's equivalent to this one that amount to say that the operator norm is bounded by a constant times a weighted Sobolev norm, and here's another s. And so what you could do is look at for instance here the smallest k that will work, or here the smallest d that will work. And the question is, if you have the smallest d that works or the smaller k that works, is it actually achieved, or is it k plus epsilon for every k? That's another thing that's not clear from the proofs. And for the case of hyperbolic groups, Nika showed that the optimal constant in this definition was 3/2. And but from his paper, I feel that it's in some sense not achieved. And right. So I think I'm going to stop here. That's more or less what I wanted to say. Thank you.
Questions?
So does this inequality there not mean that lambda is weakly contained in phi, or how does it go?
Yeah, I was wondering about that. That's another thing I'm not sure. So for instance, one thing that's easy to see is that if you have rapid decay with respect to the trivial representation, then you have to be of polynomial growth. That's the only way. And so then I was wondering if you have one representation weakly contained in another, if the rapid decay property is the same for both representation.
I see the other way. Pi weakly lambda. Okay.
So yeah, that's something I'm not sure. I mean, but I didn't spend that much time thinking about it.
I want to ask about this Boyer's result. So is there like maybe a new obstruction for rapid decay that's not this exponential distortion obstruction?
I don't think he gets a new obstruction, no.
So it's back to exponential distortion again. It's
Yeah.
the same reason.
Yeah.
Right.
Yeah, in fact, the way he shows that those representation in SL and Z don't have rapid decay, he uses Moses Raghunathan, Lubowski-Moses Raghunathan's result that with the exponentially distorted Z too. But he also does interesting things because, well, I didn't really talk about the Baum-Kohn conjecture. But one reason why people are interested in the rapid decay for the Baum-Kohn conjecture is because this, if you have rapid decay, this is an algebra, and that happens to have the same K theory, but is also much better behaved because it's much better behaved. And oh, my phone tells me it's time to stop. But anyway, I'll finish my sentence. And what Boyer does is that he looks at, he finds other algebras using the Harish-Chandra function that are kind of smaller than this, but they're not stable. They don't necessarily have the same K theory. But it's interesting in the sense that there are not that many algebras around that you can try. So any new one is potentially interesting, even though it's on the nose, it doesn't have the same K theory. Maybe you can have another idea. Yeah.
So from the examples, it's clear that rapid decay is not stable under measure equivalence, but is it stable under quasi-isometry?
I don't know that. Yeah. Yeah, I don't know that. Even the question of having, so I think even the more basic question of having amenable subgroup with exponential growth. I'm not sure if that's stable under quasi-isometry. Yeah. That's yeah. That's another good question. But even I don't even know if it's stable under isometries. But the methods are all stable under quasi-isometries. Yeah.
Do you know if any of these SLNKs are strongly bolic?
Yeah.
The rapid decay plus strongly bolic.
Oh yeah. So right. The strong bolicity is the condition for which is so Laforgue's result was that if a group is strongly bolic, whatever that means, it's a smooth way of being hyperbolic. So no, it's even cat zero anyway. It's if you're strongly bolic, then what he shows is that and you have rapid decay, then the Baum-Kohn conjecture holds true. And for mapping class group, for instance, the reason why the Baum-Kohn conjecture is still open is that they cannot prove that it's strongly bolic. And it's probably true. It should be true, but it's.
What about these guys? These SLNKs?
Oh, they're all strongly bolic because they're cat zero.
I see. So
Yeah.
they're implied strongly bolic.
Yes, exactly. Yeah, they're all in. For the SLNK, the rapid decay is really the last step to prove the Baum-Kohn conjecture. Yeah, because they're geometrically nicely behaved.
And the Baum-Kohn conjecture. So that would be one. That is an actual sort of concrete motivation for. I mean, if you care about the Baum-Kohn conjecture.
Yeah, 10 years ago, Baum-Kohn conjecture was fancier than today, I think. You know.
You can prove it without knowing what it is.
Baum-Kohn. That's the only chance I have of proving it. That much I can.
Yeah, for many people, that's the only chance. I agree. Yeah, but yeah, that's so. But I think the property is interesting on its own because it kind of tells you how the group structure is related to the geometry.
Okay, so it's time for tea and coffee break. Thank you, Jerry.